This is the index we are announcing today. First, we'll explain the differences between Eastern and Western architecture of the United States based on their geological features. Next, we'll give a brief introduction of Apple Park, about its site and technologies. At last, we'll talk about seismic design of Apple Park. Last week, we gave a brief introduction of horizontal buildings and high-rise buildings. In general, people prefer high-rise buildings because they symbolize higher status and power. However, in the United States, one of the geological features, earthquakes, creates a difference between the characteristics of buildings in the East and West. The Western United States, which is part of the Pacific Ring of Fire, is very seismically active. The Pacific Ring of Fire is home to about 90% of the world's earthquakes, and California is particularly prone to powerful earthquakes due to the influence of the San Andreas Fault. The Pacific Ring of Fire is one of the most seismically and volcanically active regions on Earth, and many stratovolcanoes are located there. Here's a visualization from the United States Geological Survey (USGS) for 2022, which shows the difference in earthquake activity between the Eastern and Western United States. These geological features have also contributed to the differences in built form between the East and West. In other words, the Western United States is more prone to earthquakes than the East, leading to the adoption of low, horizontal office buildings. One of the buildings is Apple Park. Apple Park is located on a suburban site totaling 175 acres, and it houses more than 12,000 employees in one central four-story circular building of approximately 2.8 million square feet. Its address is on 1 Apple Park Way, Infinite Loop, Cupertino, California, USA. It was opened to employees in April 2017, while construction was still underway. 80% of the site consists of green space planted with drought-resistant trees and plants indigenous to the Cupertino area, and the center courtyard of the main building features an artificial pond. Also, it has several cutting-edge technologies. Between each floor of the building is a canopy that juts out, mainly to protect employees from the intense California sun. Tucked within each canopy is a ventilation system that funnels air in and out of the building. Through a variety of sensors, the building can maintain a temperature of 68 to 77 degrees Fahrenheit, all by using an intake and release of natural air. Also, Apple Park is now the largest LEED Platinum certified office building in America. It is powered by 100% renewable energy from multiple sources, including a 17 megawatt on-site rooftop solar installation and 4 megawatts of biogas fuel cells, and controlled via a microgrid with battery storage. It also gives clean energy back to the public grid during periods of low occupancy. And we'll introduce deeply one of the cutting-edge technologies in Apple Park, seismic design. Apple Park is one of the largest base-isolated buildings in the world, uses technology that can reduce earthquake effects up to 80%. Apple Park's impressive anti-earthquake technology is designed to make sure that the buildings on its campus are resilient and safe during an earthquake. The primary goal of this technology is to create structures that can withstand seismic forces while remaining aesthetically pleasing. The foundation of the building comprises 692 large stainless steel saucers that allow the building to move up to 4 feet in any direction in the event of an earthquake. This movement can be likened to an ice cube on a plate that moves sideways, with the ice cube maintaining its relative position by moving with the plates. Jony Ive, Apple's chief design officer, and the late Steve Jobs, Apple's co-founder, believe that the base isolation was necessary to protect the company's headquarters and the knowledge within it. Ive spent 4 years renovating his San Francisco home to make it more earthquake resistant. According to Mr. Ive, Steve Jobs was influenced by the innovative engineering approaches used in earthquake-resistant building design in Japan. The building is designed to a performance level of minimal damage in a 2,500-year return period event. This led to vertical accelerations of 1.2 Gs on the floor slabs and the design requirement that they remain elastic and produce an insignificant amount of non-structural damage. The isolators used in Apple Park are triple friction pendulum. The triple friction pendulum with the articulated slider assembly in between of the two main concave sliding surfaces has become famous because it generates displacement amplitude dependent stiffness and friction behaviors. The triple friction pendulum is intended to produce low friction and high stiffness at small bearing motion amplitudes and peak ground accelerations respectively, to exert increasing friction and significantly reduced stiffness at medium bearing displacement amplitudes and peak ground accelerations respectively. Let's learn more about the triple friction pendulum, which is a key principle in Apple Park's seismic design. The triple pendulum isolator offers better seismic performance, lower isolator costs, and lower construction costs as compared to other seismic isolation technology. The properties of each of the isolators, 3 pendulums are chosen to become sequentially active at different earthquake strengths. As the ground motions become stronger, the isolator displacements increase. At greater displacements, the effective pendulum lengths and the effective damping increase, resulting in lower seismic forces and isolator displacements. The triple pendulum isolator's inner pendulum consists of an inner slider that slides along 2 inner concave spherical surfaces. Properties of the inner pendulum are typically chosen to reduce the peak accelerations acting on the isolated structure and its contents, to minimize the participation of higher structure modes, and to reduce structure shear forces that occur during surface level earthquakes. The 2 slider concaves sliding along the 2 main concave surfaces comprise 2 more independent pendulum isolators. Properties of the second pendulum are typically chosen to minimize the structure shear forces that occur during the design basis earthquake. This reduces construction costs of the structure. Properties of the third pendulum are typically chosen to minimize isolator displacements that occur during the maximum credible earthquake. This reduces the size and cost of the isolators and reduces the displacements required for the structure's seismic gaps. In the triple pendulum isolator, the 3 pendulum mechanisms are sequentially activated as the earthquake motions become stronger. The small displacement, higher frequency ground motions are absorbed by the low friction and short period inner pendulum. For the stronger design level earthquakes, both the isolator friction and period increase, resulting in lower isolator displacements and lower structure base shears. For the strongest maximum considered earthquakes, both the isolator friction and lateral stiffness increase, reducing the isolator displacement. When designed for a severe maximum considered earthquake, the planned dimensions of the triple pendulum isolator are approximately 60% that of the equivalent single pendulum isolator. So, this is our study plan for 5 weeks. For the next week, we will present about the foundation work of Apple Park. And this is the study plan for the other 6 weeks. These are the references we used for this video. Thank you for listening.